So today I want to start the discussion of gauge theory. Well, those of you who attended the winter school, we already had a mini course by Scott, which was, I think, a very good introduction to gauge theory, but I'll probably approach it somewhat differently. So today we'll mainly be talking about geometry in gauge theory, but I would like to start perhaps a little bit with an introduction saying what the idea of gauge theory is. Of course, one can approach it in many different ways, but one way to think about it is as follows. So we have a field theory, and in this field theory we have a symmetry. So we know that if we have a symmetry, the symmetry acts on the fields, and it acts on solutions of the Euler-Lagrange equations. Now, the idea in gauge theory is that we would like actually to identify the points on the same orbit of the group. So we would like to define some other space of fields. Let me call it F physical, or well, one can invent other names, which will be the quotient of the original space of fields by the group action. The same thing, I would like to identify solutions of the Euler-Lagrange equation. I would like to identify points on SOE L which lie on the same group, on the same orbit under the group action. So I would say that's the big philosophical difference between the discussion of symmetries as we did in the beginning of the course and the discussion of gauge symmetries. When we talk about a symmetry, we're saying, well, there is a group, it acts on the space of fields, the action of our Lagrange, and they behave well under the action of the group. And so once we have a solution of the Euler-Lagrange equations, we can act on it by the group action and we can obtain another solution. Right? So that's what we say when we speak about a symmetry. Now, when we discuss a gauge symmetry, the idea is different. We say, yes, there is a group acting on the space of solutions, but we want to identify the solutions which go to each other under the action of the group. So maybe I should point out that it leads to some technical difficulties. We saw that F, at least in our considerations, this was usually a vector space. SOE L, kind of in many examples, this was a vector space, and we discussed a little bit non-trivial topologies last time. But here what we want to do, we want to divide those vector spaces by group action. Potentially this is a dangerous procedure. So the result in spaces, typically not very nice spaces. So they may be singular spaces, and this is one of the difficulties, but also one of the applications of gauge theory. You can say gauge theory is a kind of instrument to study singular spaces. So this idea is to be implemented at several levels. In particular, we should say how it works in geometry, say which groups to choose here, what are the actions that we're going to use to build gauge theories, and of course we should say how to implement it in the variational calculus. So today I will be mostly speaking about the geometric part. Maybe towards the end we'll see what this means in variation calculus. But that's the important point to remember. So there is, of course, we choose groups of special type and so on, but then also our aim in gauge theory is different from our aim in the discussion of field series with symmetry. Okay, so let me start discussing geometry a little bit. Right. So this will go under the name of gauge groups. So the groups that we choose in gauge theory, these are huge groups. Let me give you a little bit of an idea of how it works. So the data that we need to start with are a manifold. So this is our space-time. So I will denote gauge groups by some other letter later. So here, this is just an auxiliary Lie group. And our examples of Lie groups will be as follows. So we'll discuss some very simple and in some way somewhat singular case of finite groups. So sometimes our groups will be finite groups. Or we'll discuss our favorite examples, R or S1. And as an example of a non-abelian group, so we'll be looking typically at SU2 or maybe at U2. So unitary groups of 2 by 2 matrices, determinant 1, or maybe determinant arbitrary. So the third part of the construction is a principal G bundle over M. Perhaps a remark. In case G is a finite group, a principal bundle is a finite cover with the structure group G. Let me recall how those, so already in symplectic geometry course we discussed a little bit the theory of principal bundles. Let me recall a little bit how they look like. So locally, meaning in a chart over M, the principal bundles are trivial, so it's a product of G cross the chart, and the projection to the chart is simply the projection to the second component. Now, there are transition or clutching functions overlaps. So they are defined by transition maps, Gij from the intersection of charts to the group, and we make the following identification. So the point given by the group element Ui and the point X in the chart Ui is identified with Uj equal to Ui times Gij X, the same point X but in Uj. So that's the equivalence relation which tells you how to glue the charts in the total space. Perhaps I should recall that on triple overlaps, there is a so-called cocycle condition, Jij times Gjk times Gki is equal to 1. But I guess probably most of you are very well familiar with this story, right? So that's something that you know. Maybe now some small twist. I'm not sure to what extent you are familiar with it. So I would like to define some other bundle. Let me call it p hat. So the bundle p hat will again have a fiber G, and it will be a fiber bundle again over the same base. So the same fiber and the same base. But I will change the gluing rule. So it will have a, you see this was the gluing rule between the charts. Now I will give you a different gluing rule. So the gluing rule will be as follows. Let me denote now the coordinates by h, just to make a distinction. So I should say, suppose I have a point on the overlap of two charts, I should say where I would glue this point. And I would like to glue it to hj equal to gij minus 1, hi gij x on uj. So for those of you who are fluent with this language, this is an associated bundle to P, where I consider the action of G on itself by conjugation. So maybe here I can write it. So P is G times over G, P, where the G action here is the G action on P, standard G action on P, and here the G action by conjugation. But for those of you who don't know this language, doesn't matter so much. You see, I did change the gluing rule, and I obtained a new bundle. Perhaps one remark, why am I doing it? So that's because if I consider sections of this bundle, it turns out that they form a group. So I claim, let me call it curly capital G. So sections of M p hat is a group. So do you see why? Suppose I got a section. So I describe everything locally. So a section means that here I have a map from X to the group. So I would have some h of X. Well, if I have two maps like that, I can multiply them pointwise. Now the question is, what happens if I go to some other chart? Right? So there I also have this section which is given by a different map. This map is different by this conjugation. Now I multiply on this side. But the conjugation is a group homomorphism, right? So if I multiply two elements which are conjugated by the same thing, I get the conjugate of the product. So this means that the product on charts, the naive product on charts, will agree if I apply this map. Note that nothing like this happens here, right? So here I multiply two u's, u and u prime. I go to the other side. I get a complete mess, right? So maybe let's do this calculation more explicitly. So let's say we have two sections, H, from M, say, two sections, H and H prime, from M to p hat. And in one chart, they are represented by hi of x, h prime I of x. And the product maps them to hi of x, hi prime of x. So this is just a g-valued function on the chart. Now I go to the other chart, and I have to use this rule. So it will be, let me for a moment not write the indices ij, so it will be g minus 1 g minus 1 hi prime g. Well, now I multiply them. What I get is g minus 1 hi prime g. And notice that this is exactly the image of this section under the transition map to the other chart. Right? So which means that the product is well defined on sections. So this might look rather abstract and unpleasant. So let me make a simplifying remark. Assume that either G is a billion or P is trivial. So you see, if P is trivial, this means I can choose those G's to be equal to 1. So this would be a particular choice of a trivialization, but in principle that should be possible, to choose all the G's equal to 1. Or if G is in a billion group, so then this conjugation is just trivial, right? So G minus 1 and G, they multiply and they give you 1. So, so then in this case, P hat is trivial. So P hat is simply a product G times M. And this group, capital curly G, so this space of sections of P hat, that simply maps from M to G. So these are actually typical gauge groups that we'll consider. So maps from M to G. However, sometimes this is not the case. So that's why I decided to give you also a more conceptual description. In principle, gauge groups, these are groups of sections. But very often, hopefully in most of our examples, this will be simply the groups of maps from M to a group. Perhaps one more remark. So assume that G is a matrix group. That's what we usually do. So in this case, one can also assign to this huge infinite dimensional group, one can assign to it a Lie algebra. Simply as a space of maps from M to the Lie algebra of our matrix group G. So the Lie bracket will be similar here. This is a pointwise product. So the Lie bracket will be a pointwise commutator. So xi1, xi2 of x is xi1 of x psi 2 of x. So there is an analog of this construction in this more abstract setting. For those of you who are fluent with the theory of bundles, I encourage you to figure out what's the Lie algebra of the gauge group in this more general setting. Suppose that the bundle p hat is non-trivial. So then figure out what will be the definition. So that's a definition in this simplified case. But then, of course, there will be a similar definition in the more complicated case. All right. So now we have groups. So they will be acting on gauge fields. So let's discuss the notion of gauge fields. For that, let me recall a notion of a connection in a principal bundle. Again, we already saw this notion, but let's repeat it. So theta in omega 1 p with values in the Lie algebra G a connection one form if it satisfies the following properties. Again, let me write them in a general case, and then maybe I show you how it relates to what we saw before with torus bundles. So the group acts on P, so we can take a pullback of theta under this action. Now let me write a formula and then discuss what it means. So here I'm acting by G. I'm thinking of G as a transformation of P, and I take a pullback of theta under this map. On the right-hand side, I'm thinking of values. So this is a one form with values in the Lie algebra. And if I think of my Lie algebra as a matrix Lie algebra, I can conjugate the resulting element. Or in more scientific notation, this would be the adjoint action of the group element G on the values of the one form. So this is so this corresponds to the action of G on P, and this is the action on values. And the second condition is as follows. So we have an action of a Lie group on the total space. We take the corresponding fundamental vector fields. And we would like the contraction with a fundamental vector field corresponding to the Lie algebra element theta. So theta is an element of G. And the result should also be an element of G to be just this element. So perhaps one small remark. For G abelian, the first condition becomes easier because it simply says that the connection one form is invariant. And that, I think that we saw quite a lot. So we saw those connection one forms in the symplectic geometry course. But there, usually our group actions were, say, circle actions or torus actions, which means that that's typically this condition that we saw, right? Did we? Okay. Now let me show you how this story looks locally. Well, so we have a chart. We denote coordinates there by u and x. And locally, connections, they look as follows. Again, I'm always using notations for matrix groups. The A is now in one form on the chart, these values in the Lie algebra. So you see here there are two coordinates, and we can in some way split the dependence on these two coordinates. So in particular, these two conditions, which are telling us what happens when we act on the fiber, they completely prescribe how the dependence on the fiber will look like. You see the u dependence, we just know what it is. So the dependence on x is concentrated in this one form on ui. And this is just an arbitrary. Now A is arbitrary. I can take anything. So let's do an exercise and check that actually the conditions 1 and 2 are satisfied, because I'm not quite sure whether you have a good feeling what these conditions 1 and 2 are. So let's check 1 and 2. Well, G star theta. So what should we do? In the chart, the action of the group is very easy. So this is just a left multiplication by G. Say, at least I chose it to be left multiplication. So G maps U to GU. So we have D, GU, GU inverse plus G, GU A, GU inverse. Well, so differential doesn't differentiate G because this is just a constant group element. So it's easy to check that what we get is just G, GU U minus 1 plus UA, U minus 1, G minus 1. So this is for 1. Now what about 2? So we should just apply this vector field. Now can you help me computing this vector field on the right hand side? So I need to know how it acts on U and how it acts on A. Maybe let's start with the question of how it acts on A. So how does this vector field, you see this is a direct product. What does our vector field do? Right, so this is, it acts along the fiber, right? It's whatever, left translation, or maybe sometimes people choose it to be right translation. So this is a translation on the fiber. How does it act on the base? Right, it just doesn't act. So this means that the contraction with the one form on the base is 0. Right? So this is simply 0. Now how does it act on the fiber? I decided the action is the action by left translations. So these are just now matrices. What happens when I substitute xi into du? If I act on the left, so this will be what? Yeah, some of those people who know the answer just say it. Right, if I take everything, yes, but if I take du, it acts, you see, it acts in this way. When I differentiate with respect to g, I get xi times u. Right? So this is equal to xi times u, and I get xi times u minus 1. So this will be psi. So this is from the story. Remember, we were discussing matrix group in some special session, and that's an exercise from that special. Okay, right? We have matrix. Right. That's, of course, if you are really serious about this story, yes, it doesn't mean much. But let's say there are two answers. If you're thinking about matrix groups, this means the product of matrices. Xi is a matrix, U is a matrix, Xi U is yet another matrix. Now, if you are thinking more geometrically, so you're taking a contraction of your vector field with a group element, with a differential of the group element, and you're getting actually, so this guy is sitting in the cotangent fiber at U, right? So now this guy, you are contracting there, and you're obtaining something which is shifted by U to this cotangent fiber. Here you are bringing it back with this U minus 1. So geometrically you would need to think a little bit about it. But if you do it with matrices, basically you never need to think. It always gives you the right result. So of course, these intermediate steps, you have to figure out how to make sense of them. The final result is just fine. It lives in the Lie algebra way it's supposed to live. Okay. Now maybe one more small calculation. So how does the gluing go? Suppose we want to glue two charts. So we have theta. Theta is a connection 1 form, and it is globally defined. It's defined in all the charts. So this means that we can write it in one chart is DUI, UI minus 1 plus UI AI, UI minus 1. That's the local expression for our connection in the chart UI. Or we can write it in another chart, DUJ, UJ minus 1 plus UJ, AJ, UJ minus 1. Right? But this is a global object. On the overlap of charts, it can be expressed either this way or that way. So this is on UI overlap UJ. Now, it will tell us how those local representations AI and AJ, how they will be related to each other. For that, we simply need to substitute that UJ is equal to UI times G IJ, and I abbreviated by G. So here, what we have is D UI G UI G minus 1 plus UI G AJ UI G minus 1. Now, there is a considerable difference with respect to the previous calculation. In fact, there are two. On the one hand, this G stands on the right instead of on the left. And second thing, now what is G? G is actually a function on the overlap with values in the group. So when we differentiate, right, so now this is not a constant, this is some kind of function on the overlap. So this differential will act on it. So if I try to, let me write down the result. I think it will be like this, DUI UI minus 1 plus UI, and here we'll have DG G minus 1 plus G AJ G minus 1 UI minus 1. So I leave you to check that actually that's what's going to happen. So there will be 3 terms, 1, 2, 3. And the 2 terms, that's because here we can differentiate ui or we can differentiate g. Now, well, this is equal to that. Well, this means that so this is an equation which tells you how to go from one chart to the other chart. Right? So this is AI, representing your connection in the chart UI. This is AJ, representing your connection in the chart UJ, and that's the formula relating them. Now let me discuss a little bit notation and finally introduce the gauge action. So many things are called gauge fields in literature. Probably the most global and most enlightened point of view is to say that the gauge field is a principal G bundle over your space-time plus a connection one form. But sometimes in the literature you would see that people would say that this is a local description, which is called a gauge field. So you have your space-time covered with charts, so you choose an atlas, and in this atlas you choose G-valued one forms on the charts, and they should satisfy the gluing formula with the clutching functions or with the transition functions of your bundle. So this is also a possibility. Of course, if the bundle is trivial, then these points of view to some extent coincide, and you can say that you have a globally defined one form A, which is a form on your space-time with values in the Lie algebra. In particular, if G is equal to R with plus as a group operation, so then we know that G is also simply isomorphic to R, and in this case our gauge fields are simply real valued forms, one forms on M, so just one forms on M. So one more example of the same type. If you take G is equal to S1, you can identify it with U1 sitting inside C star. So the Lie algebra is naturally identified with the imaginary axis, and you can identify it with R, right? So the imaginary axis is the same as the real axis. So here usually people still prefer to have A is a real valued form. So let me put it in this way. IA belongs to I omega 1 of M, because people usually still want to have this real valued 1 form. So in the end, the space of gauge fields will be the same. Now, what about the gauge transformations? Well, in this particular case, this group G maps from M to G, acts on omega 1 mg, and the action is simply given by this formula. Right? So G maps A to AG, and we define it as dg minus 1 plus GA G minus 1. So in this, when the bundle is trivial, you can also think that these are transformations which change the global section, the globally defined section. So you have two trivializations of your bundle, and this formula would identify A's in two different trivializations of your bundle. So, for those of you who never done it, check that this is an action. Let me write it more explicitly in these two examples. So first of all, the example of G equal to R. So what will be this, this action? First of all, right, R is abelian, so there is no conjugation. Conjugation is trivial. Now, we should write this GG minus 1. Maybe it's not very comfortable to do it for the additive model. So let's note that this is the same as R plus non-zero. So the multiplicative group of real positive numbers. And then what we can say G of exponential of some parameter V exponential minus V. Right? So that's how this formula would read if I use this multiplicative model. And this would give you A plus dV. Right? So in a similar fashion for S1, so I write IAG, again, no conjugation. And here, well, I should take some unitary complex number, right? So D, for instance, exponential I theta, exponential minus I theta. And this is equal to I A plus d theta. So where theta comes from a map from our manifold to G, and G is S1. So we'll discuss it in a bit more detail during the next hour. But so for a moment, what we've done, we have gauge groups and we have gauge fields. Maybe let me add one more exercise. So again, for those of you who are fluent with the geometry of bundles, so this is the formula for the gauge action in a trivial bundle, right? So now, what is the action? What's the action for P non-trivial? All right, let's have a break. Let's continue. So let me, for a second, go back to our philosophy. So we have the gauge group, which is supposed now these are gauge groups that we discussed during the last hour. So they will be acting on spaces of fields. And so there is a quotient, so the orbit space that we call physical. And in fact, as I mentioned, this is typically a complicated space, right? As almost any quotient space, when you have even a vector space or some relatively simply described space divided by group action, usually you get something complicated. So one of the ideas of how to describe quotient spaces is by sections. So suppose we're trying to define a section which, let's say, at least locally, meets every orbit exactly once. Of course, well, this disclaimer, at least locally, it more or less kind of annihilates the rest of what I'm saying. But still, this is our intention. So that's one of the ways to study F physical. We'll now look at some simple examples. Let me just say that in the physics language, such sections are called gauge fixings. So a gauge fixing is a section from F physical, from the quotient to the space of fields, which meets every orbit exactly once. So let's look at examples. The first example, M is an arbitrary manifold. I take G, the additive group, or, which is the same, positive real numbers with a product. We know that in this case F, well, maybe a comment, P, a principal bundle with a contractible group is always trivial. So this means that the space of gauge fields is simply omega 1 of M. And the action of the gauge group is by adding a differential of V, where V is a map from M to R, right? So that's our definition of the gauge group. In other words, this is just a smooth function. So what is this quotient space? F physical? Well, here it's easy to say. It's omega 1 of M divided by omega 1 of M exact. So this is still a nice vector space. Perhaps to make this example even easier, let me make a specific choice of M. So the example 1 prime. Let me choose M to be equal to S1. So in this case, what happens? So this F physical is omega 1 of S1 divided by omega 1 S1 exact. But since 1 is the top degree, so all these 1 forms are closed. So this is actually just by definition the Durand cohomology of the circle. Well, the Durand cohomology of the circle in degree 1 is R. And perhaps let's look at this very simple example in just a little bit more detail. So suppose we have a connection or gauge field, a 1 form on S1. So let's define an explicit map to R. Would you have a suggestion? So given a 1 form on a circle, how do you compute its cohomology class viewed as a real number?
Integrate.
Right, absolutely. So let's map it to the integral. And it turns out that with some, here I set up an isomorphism in some way. For instance, I can set it up in this way. So this would be a particular way to set up an isomorphism between cohomology and R such that the projection map would be exactly this integral. So that's actually the natural projection map. Now, what about a section? Suppose I'm given a real number, alpha, and I would like to build a connection, build a 1 form with exactly this integral. So in fact, sections are typically many. There is not one canonical section, so you can make a choice. So here we're making a choice of a gauge fixing. So what would be your favorite choice? Or what would be, can you come up with a choice?
Something like alpha d theta.
Right, so maybe 1 over 2 pi if you want the integrals to agree, and if the length of the circle is 2 pi. Of course, if the length of the circle is 1, then right. So this is a section. Now let me look at another example which is very similar in nature but which gives different results. So let me take M to be S1 again and G to be also S1. Well, F physical is equal to the space of 1 forms modulo the gauge transformations. A goes to A plus d theta, where theta is now a map from S1 to S1. So what's going to change? Will it change? Or is it the same? Let's make the following experiment. Here we define a map from omega of S1 to R by the integral. So let's see what happens with the integral if we change the if we change A by a gauge transformation. So integral of A plus d theta over S1 is an integral of A over S1 plus an integral of d theta. So what's the integral of d theta for theta map from S1 to S1? Right, this is the degree, probably maybe times 2 pi, right? Right, depends how we set it up, but if the circles have length 2 pi, then this will be 2 pi times the degree. So times degree of theta. That's correct. In particular now, this means that this map cannot be a map to a physical, right? Because it changes on the gauge orbits. Now claim a physical is again a circle, a quotient of r by 2 pi z. And you can also think about it in the following way. If you are more conceptually minded, so this is a quotient of h1 of S1R, the space that we had before, by the image of h1 S1Z mapped to h1 S1R. So that's this lattice 2 pi z that we obtain, that the image of the integral cohomology in the real cohomology. So perhaps one more remark about it. So we can still define the projection map. So A in omega 1 S1. But now, of course, the integral wouldn't do. We need to get rid of this 2 pi z ambiguity. And the idea is to take the exponential of this integral. It kills exactly this ambiguity. So this is an element of S1. Which is now F physical. It turns out, and maybe I leave it as an exercise, so there is no global section for this map. You can build local sections. For instance, you say that this is exponential of I alpha, and you map it to 1 over 2 pi alpha dx, as before. But of course, if you go around the circle, then your alpha will start at 0 and will return to 2 pi. Exponential of I alpha 0 is equal to exponential I alpha 2 I 2 pi, but the representatives will be different. So you can build local sections. You can introduce charts on your F physical and build local sections over these charts, but you won't be able to build a smooth global section. So this is an example of how it works in practice, and actually, even physically, this is an important example. So now one more small section. Gauge invariant quantities. So if you want to build some gauge theories, we need to have some tools to create gauge invariant quantities. And let me give you some simple examples. Of course, probably most of you know it already. So if G is abelian, for instance R or S1, we know that A will be in one form on M, and gauge transformations are just adding exact forms. So then we can introduce Fa to be simply the de Rham differential. So this is a two-form on M, and FAV is D, A plus DV is equal to dA and is equal to Fa. So this two-form is a gauge invariant quantity, and this is an important consideration. So maybe some names for it, right? So in mathematics, it would be called the curvature of A, and in physics, it will be called the field strength. So again, for those of you who attended the winter school, you heard a lot about this story in the lectures of Jeffrey Scott. Now, let's say G is non-abelian, for instance, SU2 or any other matrix group. So if the bundle is trivial, gauge fields are one forms with values in the Lie algebra. And the gauge transformations are somewhat more involved. So let's define again the curvature or the field strength. So I hope that with my choice of signs here, as usual, with left and right, there is a choice of signs. So for matrix valued, for matrix groups, the definition would be dA minus A squared, or maybe a somewhat more enlightened way to write it down is dA minus 1/2 commutator of A and A. Note that here it's since A's are odd objects, so this is an anti-commutator, which means that in fact, by definition, this is A times A plus A times A, which explains the equality between the two definitions. So this is more conceptual because you can make sense of it also for non-matrix Lie algebras. Now the standard proposition f of AG is a conjugate of FA by G. Even though probably most of you know it, let me just make a one-line calculation to prove it, just for you to see again how those calculations work. So FAG, this is DAG minus AG squared. And this is D, DTG minus 1 plus G, A, G minus 1 minus so this is a huge expression. Let's work out how it looks. So first of all, here, let me recall, we did this exercise several times. So we take a differential of this dgg minus 1. This is also called the Maurer-Cartan structure equation, right? So d changes sign, passing through this dg, and differentiates g minus 1. d of g minus 1 is minus g minus 1 dg g minus 1. So in total, we get dg g minus 1 dg g minus 1. So that's the differential of the first term. In other words, the square of dg g minus 1. Plus, let me write it in the following way. dg g minus 1 ga g minus 1. You see, I introduced this extra g minus 1g for convenience. Plus g dA g minus 1. And then plus ga g minus 1 dg g minus 1. Explain me this sign. Why is it plus? So what happened? Well, how did?
You get a minus sign from the g first, and you get a minus sign from going past the a.
That's right. So there are two minus signs. They compensate each other. But you see, that's a kind of complicated game. So minus this thing, which is dgg minus 1 squared, minus dgg minus 1 gag minus 1, minus gag minus 1 dgg minus 1, and minus ga squared g minus 1. Just a small test question how this thing came about. Right? There were many g's. Now there are not that many. Right? So this is the square of gag minus 1. We agree on that. Now, so the lucky cancellations, this cancels this, that cancels that, and so basically almost all the terms disappear to give ga minus a squared g minus 1. Again, that's something that you can do as we did in 3 lines. You can also do it conceptually, understanding why curvature is a good object on a principal bundle. So that's also, of course, a very nice calculation. But maybe for today, I prefer to do it this brute force way, which is actually quite efficient. All the terms cancel, you get the result. Now, corollaries of this proposition. So again, we pretend we have matrix groups. So take a trace of some power of Fa. So this is an element of omega 2m0 of m times the space of gauge fields. And it is G invariant. So why is that? Well, that's because the curvature or the field strength, it just gets conjugated by gauge transformations. Now, if you take a power of it, it will also get conjugated. When you take a trace, it will remain invariant. So and that's a very important observation. Another important observation, fix a Riemannian metric on M and consider trace of FA times star FA, where star is defined by the metric, so the Hodge duality. So this will be in omega n, right? So omega in the, so the dimension of the manifold M, 0 M cross F, is also G invariant. So these quantities, they have names. So this one is called the Young-Mills Lagrangian density. So we're going to look at it in detail. So those are called Chern forms, and they define Chern classes of the principal bundle on your base manifold. In fact, one also uses a little bit Chern forms in gauge theory. So we'll probably see examples where Young-Mills forms and Chern forms are mixed. Some more examples of gauge invariant quantities. So let's say G is equal to R, and let's choose a map from a circle to our space-time. So let's denote the image, so the curve, the parameterized curve, by capital gamma. So then let's consider an integral over gamma of A, or this is the same as the integral of the pullback of A under this map small gamma over the circle. So what we discussed before, right? In a gauge theory on a circle with the gauge group R, the integral of the gauge field over the circle is actually projection to F physical, which by definition means a gauge invariant quantity, right? So this is a function on the quotient space, right? So F physical of the circle. But this means this is a gauge invariant quantity here as well. I'll let you check it. So we have a gauge theory on the ambient space. We restrict it to this curve gamma. On the curve gamma, gauge transformations act in the same way. There we know the gauge invariant quantity. It's this. So hence this is a gauge invariant quantity. Similar story for G equal to S1. So there we know that we should take exponential of I integral gamma, or exponential I integral S1 gamma star of A. And here, well, there is some other standard notation, W gamma of A. So this is a non-local gauge invariant quantity which depends on the curve and on the gauge field. In physics, this would be called a Wilson loop or Wilson line. But for us, this is an S1 invariant quantity. And here, we know that this is an element of S1, which is identified with the F physical of the circle. So we're using the restriction of our gauge theory from the manifold to a curve, and on the curve we actually know we already computed F physical. So this means this allows us to construct a gauge invariant functional on the original space. Right. Okay. So we spent lots of time on geometry. So let me end up this hour with a little bit of variational calculus. Right. So let's go back to our story. We have the space of fields, whatever it is. We have a group. Say we probably want to use gauge groups, but we have a group acting on it. And we say it's a symmetry. Symmetry, I recall, this means L of psi f of the Lagrangian is equal to d alpha psi. For all elements of the Lie algebra of our gauge group. This actually implies that G acts on sol EL, right? So that we proved. So that this is the this situation for any symmetry. Now let me also recall that we have Noether currents, which are defined as iota psi f gamma plus alpha of psi Noether currents. And the Noether theorem was saying that dj of psi on sol L was equal to 0. So that's what we got from our first classes. Now, definition. So G acting on F is a gauge symmetry. If in addition to this condition on the Lagrangian, we have the following condition. So J of psi on sol L is not only closed but also exact. So there are beta of psi's such that the Noether currents are total derivatives. So I must say that this is a definition that we were debating a little bit with Pavel over the last days, but okay, let's say that's our starting point. So that's the definition, our definition of gauge symmetry. So the Noether currents turn out to be exact. Let me discuss a little bit what are the corollaries of it. And then next time there will be plenty of examples So what are the properties of this definition? First of all, let me recall that in the case of M equal to R cross sigma, where sigma has no boundary, we have a notion of Noether charge, which is conserved, and which is simply the integral of a sigma of j of psi. So this is the well, in our case, if the Noether current is actually exact, we get integral of a sigma of d beta xi, and we get 0. So it turns out that those conserved Noether charges in gauge theory, they simply vanish, right? So actually, I tried to sell you the Noether theorem saying that, well, it's great, right? We have a symmetry, and because of that, we have conserved quantities. Now, here it goes the other way around. These quantities are certainly conserved, but they're all 0, right? So it kind of, at first sight, it sounds as a bad news. But, well. Now, the second consideration. Recall that we had the two form defined on Sol EL. So closed two form on Sol EL, and we proved the following theorem, saying that J xi f omega is equal to minus delta q of xi. So we had such a formula. Now, if the Noether current vanishes, this means its differential vanishes. And in the case of gauge theory, so this is simply equal to 0. It has the following consequence. If we compute the Lie derivative of omega, this will give us delta J xi f plus J xi f delta omega. And both terms now vanish because J xi f omega vanishes by this equation, and delta omega vanishes anyways because omega is a closed two form. Right? So this is now, in gauge theory, this is now 0. See what happens. For omega, we have the Lie derivatives, and contractions with fundamental vector fields vanish. So such forms are called basic. So omega is a basic form on F with respect to G. And assuming that G is in some way connected, this tells you that omega descends to F physical. So let's call it pi. Connected. This implies that there is omega physical a two form on F physical such that I star omega physical is equal to omega. Of course, here one should probably take this notation a little bit with a grain of salt, because before we were talking of differential forms on some infinite dimensional vector spaces, and in principle that's okay. Now we're talking about differential forms over quotients. So here probably one, strictly speaking, needs to say what that means. Say over some smooth points of F physical in general. Now, here is a question for you, whether we've seen such things somewhere in the symplectic geometry course. So where do such equations appear?
When we do reduction.
That's right. So let's compare to reduction. In symplectic geometry. So there it worked as follows. We had a symplectic manifold with a moment map. And here inside was sitting the fiber, right? Maybe let me write it in the following way. It was sitting the fiber together with the form restricted to the fiber. And from there was a projection to the fiber divided by the stabilizer, which was the reduced space at x with the symplectic form omega x. Right? So that was the situation. Now, how does this situation in gauge theory look like in comparison to what we have here? In principle, it looks like this fragment of the picture, right? So a priori, maybe we don't have this ambient symplectic space, but what we have, it resembles to a fiber of the moment map. So we have our space Sol EL. It has a two form. This two form is closed, but already from this equation, it's clear it cannot be non-degenerate in any sense because it has a huge explicit kernel, right? So here, this kernel were the vector fields, right, by one of the propositions in the symplectic geometry course. We had the kernel equal to the action of the Lie algebra of the stabilizer inside the tangent space to mu x, and then it would descend to the reduced space. So this picture resembles, so like maybe the parallel picture here would be, so we have Sol EL together with the form omega. This is all acted by G. And here we have Sol EL physical, which is Sol EL divided by G. And we have the form omega physical. So that's the parallel. That's the parallel to this story. Now, we said that the Noether charge vanishes. So in fact, the Noether charge should be compared to the moment map, right? For instance, if you take the fiber of 0 here, so then restricted to this part, the moment map would vanish, right? So this Q, and of course Q satisfies the moment map equation. So Q is like a moment map. Sol EL in gauge theory, that's like the fiber of 0, and the reduced space, they Sol EL physical. So maybe I should also say that the hope is omega physical non-degenerate in some sense. If Sol EL phys happens to be finite dimensional, then it is just not degenerate. If so, L is infinite dimensional, you have to negotiate what's the meaning of it. So I would like to stop here for today. So next time you will see lots of examples of this structure that we saw in the end of the lecture, of course using the constructions of the gauge fields. And maybe that's also an occasion to say that since I won't be here for the next 3 weeks, so I leave you in the safe hands of Pavel, who will be teaching the next 3 classes. Okay. Well, that's it for today.